Hello and welcome to space. This month we're getting all revved up about rocket engines, powerful, precise machines that take men and satellites into orbit. We're going to see how they're made and how they're tested. But first, some other news from the universe this month. Scientists say the newly awakened Philae lander could begin low-energy experiments on its comet once it has a stable connection to Rosetta. Construction is to begin in Chile of the giant Magellan telescope, the biggest optical telescope ever built. It will offer images of the faintest objects in space. And new Earth observation satellite Sentinel-2A flies into orbit this month. Its colour vision cameras record key data on agriculture and forestry. To our main story now, and an insight into how rocket engines are made. It can take years to build a rocket and just a few seconds for it to launch. It's a moment of drama when immense forces are at work.
To get to space you need a lot of power. To overcome the gravity of the Earth you need a lot of power.
That power to put men and machines into orbit comes from rocket engines, burning either solid or liquid fuel, or both in the case of this Ariane 5.
5, 4, 3, 2, 1, 0. At that moment, we start the turbo pump here, which pumps the hydrogen into the combustion chamber of the Vulcain engine, which is the first engine to fire. Once we've checked it's working properly for about 5 seconds, then we light up the 2 solid fuel rocket boosters alongside. And then, off you go, the rocket takes off.
Before anything can take off, it comes through here. This is the site of French rocket engine producer Snecma, a factory complex tucked away in the forests of Normandy near the town of Vernon. Sitting in a valley lies the test tower, where the engines are first sparked to life, generating clouds of steam.
All the engines are tested here when they come off the production line, with tests that last several hundred seconds. It started once here and the second time is on the launch pad.
3 rocket engines are made at this site: the Vulcain 2 used on the main stage of the Ariane 5, the smaller HM7B used on the Ariane 5 upper stage, and the newer Vinci, which is still under development. They all work on the same principle of accelerated gas creating thrust through a nozzle.
The spinal column of a cryogenic engine these days is the combustion chamber, which is here. We have the combustion chamber followed by the part known as the nozzle, where the gases accelerate and create thrust. The final essential part of this engine is what we call the gimbal joint, which is up here. The engine is fixed to the rocket by this piece, which transfers all the thrust and makes the rocket lift up, and also allows it to steer, orientating the engine along different axes.
Many of the components are made elsewhere in Europe and then assembled here. However, the vital fuel pump for each engine is fabricated at Vernon. One by one, the pieces are carefully milled from titanium or lightweight alloys over a period of weeks, a process overseen by engineers like Emily Demille.
In the Snecma factory at Vernon, we make components like this, which is the hydrogen turbo pump for the Vulcain engine on Ariane 6. So you can see here a workshop with very precise machines to make components with a precision in the order of a micron.
These precise and expensive machines still need to be adaptable to meet changing demand from customers and challenge innovations from competitors. So the workhorse heavy-lift Ariane 5 is going to be replaced by this, the Ariane 6. It's designed to be flexible and will be available with either 2 or 4 boosters to launch either 5 or 10-ton payloads.
Ariane 6 is the logical follow-up of Ariane 5. Where the main element, you could say, is that the cost of bringing 1 kilo up in space will be 50% of the present situation with Ariane 5. We are using technologies that are already developed or almost developed. Look at the engine. We are using the developed engine for Ariane 5. We upgrade it, we make it better, but we are using the same principles. We are using a booster that will also be used on our small launcher Vega in the future. So we make commonalities between launch systems.
While the market may evolve, the bare facts of this unique business are unlikely to change. To get to space, you need a lot of power.
Thrust is 135 tons, around 4 Airbus A320s, with a flow rate of 300 kilograms per second, which is like 2 bathtubs being emptied per second.
So each journey into orbit begins like this.
It's an enormous excitement. You see the emotion of people that have been working on towards that moment, that they really see the launcher lifting off. And that's an emotion. It's much more than technology and work. It's an emotion to see that it works.
An emotion reinforced by the fact that each launch is unique, and for the moment at least, each rocket flies to space just once. Now, to our regular update from the Astronaut Academy in Cologne, where Alexander Guest tells us what it's really like to come home from space.
0.06, range ring. Target is normal.
It really feels like a roller coaster ride, like the best one of your life. In order to get into the atmosphere safely, you have to separate your spacecraft in 3 different parts. You have explosive bolts that kind of violently rip your spacecraft apart. When you start hitting the atmosphere, you actually see the other parts burning up. And you can not only see that, but you can see yourself burning up. You can see little parts of your own spaceship disintegrated, melting up and kind of flying, accelerating out in the plasma, glowing red. So you really pushed in hard, it's hard to breathe, and your tongue wants to get pushed back in your throat. So it's really a tough time. When you're under the parachute, you have about 10 minutes to prepare for what comes next, and that is the landing, which is pretty rough. It feels like a little car accident.
That's it for now. Next month, we'll be reporting on the mind-bending science of gravitational waves. See you then.